Hi all. Over the weekend I wrote a quick program in Java to kind of test the efficacy of the genetic algorithms that we learned about this week. So here's some of the parameters. Right now they're just hard-coded as constants in the program. So the first is how many generations it's going to run for. So I put 600. It shows 600 somewhat arbitrarily. If I choose too high, it starts having some memory problems and starts getting bogged down. 600 seems to be a pretty good number. Then there's the initial size of the population. Again, I just kind of started with 10. Oh, no, sorry, I lied. The init pop is the initial population. I started with 100. Init size is the length of the bit strings as they started. Theoretically, this could change. The easiest way to change is if I actually turned off the even crossovers. That would allow crossovers of different lengths, and therefore things could get really big. Right now, the even crossover is set for true, so if it weren't for mutations, it would always stay length 10. But one of the things that mutations can do, it's unlikely, but is a position in the string could be deleted, in which case it would get shorter, or it could be inserted. The odds of it are relatively small. If there are, it starts with length 10, so generally there's an equal probability that any one of those 10 things will stay where it is but just get toggled, from actually not even toggled, just get set randomly be 0 or 1, which might even stay the same. However, there's also an equal possibility that the string could grow or shrink. So it's actually a 1/12 of a probability for each of the 10 positions, an additional 12th that one of them chosen equally at random might get deleted, and a 1/12 chance that there might be something inserted in there. So the longer the string gets, the less likely it is to grow. That's the upshot from all this. Then there's the incest number. So he talked about this in class. He didn't call it incest, but basically this setting is how far back in the duration it goes to see if you have any relatives in common. And if you do, your kids, you just aren't allowed to have kids. So that's basically that. It's really interesting when it's set. This makes a much larger difference than you might think, and I can show you some examples of that. But anyway, let's go with these settings. And what I was curious about was, I thought the idea of genetic evolution, genetic algorithms were really cool. I like the way it mimicked evolution and biology. But at the same time, I'm thinking to myself, this can't really work, right? I mean, it's not going to be that much better than just randomly choosing your strings. So I was kind of curious to actually check that out. So let's actually see. So I made a graph here. So this is at generation 0 right now. So these are the 100 just randomly decided bit strings, all of length 10. And the fitness function in this case, I actually have the program set up that can handle 7 different kinds of fitness. Actually, let me go back to the program and show you the 7 different kinds of fitness. Here we go. So the 7 different kinds are, you can just count the number of ones in the bit string. You can count the number of blocks of ones in the bit string. You can count the number of consecutive, the largest number of consecutive ones. In other words, basically the size of the largest block, whereas this one counts the total number of blocks. There's counting, you're more fit if you are half ones, and there's 2 versions of that. There's the one where having half ones is more impressive or more fit the longer you are, and there's one where it doesn't matter your size. And then there's also how many ones you have at the very front. And then there's a very boring fitness function, which is just your length. I guess for this first run through, I just did it as fitting consecutive ones. So, all right, let me go back to the graph. So this fitness score is based on the number of consecutive ones you have. So it looks like most of them have 2 or 3 consecutive ones. And wow. There actually was one that had all 10 consecutive ones. Imagine that. So yeah, I'm a little surprised at that. But anyway, it was random. So let's see how this changes as time goes on. So I ran it for 600 generations, but this particular program I'm using isn't really meant for rendering histograms very quickly. So I'm using GeoGebra, by the way. So I actually only had it print the histogram or display the histogram every 10 generations. Then it'll print the generations up here. So, all right, well, let's see how this is going. Just to give you an idea of what you're going to see, notice how right now it's kind of got this long tail. You're going to end up seeing that this tail, and I ran this program many, many times, so I just kept seeing this pattern. This tail shrinks very, very quickly, okay? And the other thing that happens is there's huge jumps in the beginning, in the first few generations, and then less so and less so. But all right, let's just run it and you can kind of see what's going on. So I'm going to click animate here and watch the generations tick up. Notice it made a huge leap with those first 10 or 20 generations. And now it's just kind of fine-tuning it. Every once in a while a new one will crop up here, and then more and more and more as it propagates out with this fitness. And it's going to go until it reaches 590. I did 600 generations. The first one was generation 0. So this is it. This is where it ends. The last one that got printed. So notice it started down here with a lot of 2s and 3s fitness, and ended up, there's actually one that looks like it's got a 22 fit. Oh, I guess actually it's set right now to be left binned. So actually this is a 22, not a 23. So no wonder I was surprised when I thought there was 10. It was actually only 9. But seems like there's a huge amount of 21s. Notice the standard deviation is much less than it was at the beginning. It's kind of getting clumped around these higher numbers here. So, all right. So now the question is that any better than if we had just done randomly? So in order to be fair, I gave randomness every single chance. So what I did is however many total number of individuals are created over these 600 generations. And let me go back and actually check in the program. I had it print out in the actual program. So it actually made 11,057 individuals. So what I did is, to give it a fair shot for the randomness, I let it make that 11,000 number of individuals. And it's only going to take the best 100 of those. Oh, also in terms of the length. So again, in order to really give randomness the fair shot, I said, okay, whatever the highest length of things were here, which I think ended up being 22, I made every single one of those 11,000 be a length of 22. So keep in mind, I don't know when it first hit length 22, but that took hundreds and hundreds of generations, I'm sure, before it hit a length of 22. So for the randomness, I made it to 11,000, all at length 22, plotted the top 100 fitnesses. And when I click here, it'll show the result of that. It's down here. And notice it had that same sort of shape of the distribution as the generation 0 did. No surprise, because that was also randomly determined. Just of length 0, or just of length 10 rather than length 22. But it's got that kind of big, heavy right skew to it right here. But notice the the median length here, I don't know if it's the median or not, but certainly the modal length is like around 10. So 10s, 11s, 9s, 10s, 11s are the fitness here for the top 100, deciding randomly, as opposed to when we did the evolution here. I'm actually going to reset this and animate it again so you can see right away. Actually, that went a little fast. Let me reset it one more time. So if I just jump 10 generations, it's arguably already better than the randomness. I guess this is 20 generations. So yeah, it turns out the randomness did kind of surpass a little bit, but keep in mind, this is based on a size of 22, length 22, and 11,000 members of length 22. So again, I just go another 10 generations, maybe a little bit more. And let's just go till it totally surpasses. Yeah. So at this stage, by 200 generations, the worst of the genetic algorithms are better than the best of the random. And then, of course, by the time we finish up all 11,000 ones, which is how much the randomness had, it's way better. So despite my initial skepticism, it does look like genetic algorithms are noticeably better than just doing that amount with that length a random number of times.